Now that we have examined the properties of logarithms and exponentials, let's go ahead and look at how we can apply properties of these to solve equations. So let's look at solving logarithmic equations. So first off, let's look at a function, log base a of x, and determine if that is 1 to 1. In either case, if a is bigger than 1 or if a is between 0 and 1, we only have two possibilities. If a is bigger than 1, our function is increasing. If a is smaller than 1, our function is decreasing. And in either case, our graph passes the horizontal line test, so f is 1 to 1. Because f is 1 to 1, we can go ahead and use the definition to determine a property of the logarithmic function. So if we look at this statement, f of x1 equals f of x2, that would be the same thing as log base a of x1 equals log base a of x2, and that would say that we are guaranteed that the inputs of the logarithms are the same. So we can rewrite this so that we have the 1 to 1 property of logarithmic functions. So if we have two logarithms that are equal, that have the same base, then their arguments must also be equal. So there are various approaches we can take when solving a logarithmic equation. We can convert logarithmic equations to exponential equations. We can use the 1 to 1 property of logarithms that we just determined. We can condense logarithms. We can use the change of base formula. But at the end, we must always check to make sure that our solutions are not extraneous. In other words, we must always make sure that our solution does not make a logarithm undefined. In other words, we don't want an argument to be negative or 0. So let's solve this equation. Log of x minus 3 equals 2. So here we do not have two logarithms, so we can't use the 1 to 1 property. Let's go ahead and just convert this to an exponential. So it might be beneficial for you to think of this so that you can see the base. The base is not written because it's a common logarithm. So we know that it means that the base is 10. So let's convert this to an exponential. The base of our logarithm is 10, so the base of our exponential will be 10. The exponent on 10 will be found on the other side. So we have 10 squared, and that is equal to x minus 3. So we have 100 equals x minus 3. So 103 equals x. And we can substitute this value back in the original logarithm, and we would have log of 100, which is acceptable. So log of 100 would equal 2. That is correct. So this is our solution. Now here we have a logarithm equals a logarithm. So that kind of tells us that we probably will be using our 1 to 1 property. But before we go that direction, we have to deal with this 1/3, because the 1 to 1 property means that the only thing on the left-hand side is a logarithm, not something times a logarithm. So let's bring that 1/3 inside as an exponent. So we have log base 7 of 2x minus 3 to the 1/3 equals log base 7 of 9. Now we have two logarithms that are equal and they have the same base, so their arguments must be the same. Now, that 1/3 exponent is the same thing as a cube root. So we can undo that cube root by raising both sides to the 3rd power. So we have 2x minus 3 equals 9 cubed, which is 729. Let's add 3 to both sides. And so x equals 366. Now, if we take 366 and plug it back in for x, this argument would not be negative, so we are okay. Here we have multiple logarithms. In particular, we have 2 logarithms on the left-hand side. So we can't jump straight to using the 1-to-1 property, because that would mean that we would have just a logarithm equals a logarithm. So can we take this left-hand side and rewrite it so that we only have one logarithm? Yes, let's condense it. And so we are subtracting 2 logarithms. So what we can do is we can divide their arguments. So we got to have x plus 3 over x. We're taking the natural log of that. Then on the right-hand side, we'd have just natural log of x plus 5 rewritten. Now we have 2 logarithms that are equal, so their arguments must also be equal. So x plus 3 over x must equal x plus 5. So let's multiply everything to clear the fractions. So what we can do is multiply through by the denominator x. So we'll take x plus 3 over x and multiply that by x. But if we do that on the left-hand side, we must do that on the right-hand side. So x plus 5 will also need to be multiplied by x. So we'll distribute on the right-hand side, and on the left-hand side, the x's just cancel. So we have x plus 3 equals x squared plus 5x. This is quadratic, so let's get one side equal to 0. And so we have 0 equals x squared plus 4x minus 3. This does not factor, so we'll have to use the quadratic formula. So x equals negative 4 plus or minus the square root of 4 squared minus 4 times 1 times negative 3 all over 2 times 1. So we have negative 4 plus or minus the square root of 16 plus 12. That's all over 2. So we have negative 4 plus or minus 2 square roots of 7 over 2. So we can factor out a 2 from the numerator. And now cancel the 2's. And so this means that x is going to equal negative 2 plus the square root of 7, or negative 2 minus the square root of 7. Now, let's start with negative 2 minus the square root of 7. This is a negative number. If you want to, you can put this into your calculator, and you will see that it's about negative 4.6. If we put negative 4.6 in, well, this argument would be negative, because it would be negative 4.6 plus 3, that's still negative. And indeed, this logarithm would have a negative argument as well. So it only takes 1 to spoil it. So negative 2 minus the square root of 7 is extraneous. However, negative 2 plus the square root of 7 is about 0.6. Well, if I add 3 to it, that still will be positive. 0.6 is okay here, and 0.6 plus 5 is still going to be positive. So we're okay for each one of these logarithms. So it is an okay answer. So x equals -2 plus the square root of 7 is our answer.